Welcome to part 3 of the disassembly tutorial. So we extracted the main part and now we want to continue and analyze the main part like we did it for the bootloader. When we dumped the main part, I saved the whole memory area starting at the original bootloader address until the end of memory. And what we can do now is we can import this raw file. And this raw file shall actually replace the existing segment that we have because it contains the same memory location. So the expectation would be that still at 1900 there is the bootloader and that we can keep all the user equids. So if I say yes here, it asks me this raw file, where does it start? And I say it starts at 1900. And we can check the user equids, they are still there. So they are carried over from the bootloader. So some of them may still be valid, some maybe not. And what we see is, oh pity, there at 900 there is no code anymore. That means after the bootloader completed loading, it started the main program, and because booting is over, the main program has restarted reusing these memory locations, which is natural if you think about that SynCalc was designed to run on a 48K machine, so every byte is valuable, and if you're done with loading, you can use the bootloader area for something else. So what could be this something else? Let's see. Well, there are zeros, and there are inverse things, and these definitely looks like some numbers. If you have seen a number of disassembly sections, you will get familiar with this and recognize these patterns. These patterns indicate that this is screen memory. So let's turn it into screen memory. And we see that this is actually obviously the header area of the SynCalc screen. We can also switch here to screen display. That makes it more obvious. Yeah, so we can switch between ASCII and screen display. And here we see then, of course, probably at the page boundary A000, there the screen memory will start. Yeah, so as you may remember, screen memory must be aligned to 1K boundaries, so it's very likely that it starts here. And of course the screen is longer. Oops. Oh, what's that? My mouse is too fast. So let's see what we have here. Option, and it ends here. Probably. Oh, maybe it also ends here. Menu. No, menu still belongs to the text. I actually see here at DC1DCO there a display list starts. So let's scroll up a little, not becoming too fast, and say that all of this is now screen memory. And we see that some of the labels that we had defined before, they are now no longer valid. Yeah, so this read sectors and this print byte is something that was there when there was a bootloader, and now they are no longer valid. So we should go there, and everything in the area of 1A and 1C where there is screen RAM now, we should delete because we know they cannot be relevant anymore. So let's delete them. Yet still we see here there was the display list, and actually what we see here 707070 421A, this is again the begin of a display list. Yeah, so the display list is there where it was during loading. That's also rather obvious because the screen that we see during loading, it remains. So we turn this up to the end of the display list, which is always 41 and then the target address. We change this into display list. Yeah, and we see that these labels that we had defined before, they still appear to be valid. Okay, then the actual code starts at 1E00. That is what we saw in the bootloader. So this is some unused space. So I'll call it data store. make it unused space. We see there are some references to it, so maybe it's not fully unused, so it's used as a buffer for something. And then here the actual main code starts. Here we have the label that we had defined in the bootloader. But the main part doesn't seem to start with reasonable code, but now I switch to display again. It starts with ASCII, and it starts with the word syncalc, terminated with an inverse character. So this is obviously string. This is something that's used by as an indicator to see where the program starts. And it's also an indication that the file version, this is the original start and load address of the file version. And everything that was before is just some kind of bootloader. Now, when we scroll through this memory area, which is huge, we come to the end around 3000. And in the bootloader, we had seen that it loads up to 3000. So everything beyond 3000 cannot be code. It must be some kind of data. Then we had here previously screen memory, and I still see some screen memory data in here. So maybe we turn this into screen memory. Not sure if it's still used as screen memory, but from the content, it still looks like screen memory. Again, this is 1K, 4 pages, and we turn them into screen bytes. And we see the text that we had seen during loading. And then we see at 4000 a certain pattern starts, and we know from the fact that syncalc uses extended memory, and extended memory in the Atari is between 4000 and 7FFF, that everything in that area must actually be data space. Yet we see, and this is now a particular property of syncalc, we see a lot of labels that are defined here. So how come this DIS6502 thinks that these are labels? They are indications that there is some part later on here that thinks that this is a label because it's interpreted as code, but also when you look at this code, you see that this is crap. This is not code. And this is a nice coincidence because instead of being code, we see what it is. We see these are ASCII characters, namely these are the format. These are the statements that are supported in syncalc. So we know that all this is actually text. And because text starts in the ASCII area at 40 up to 7F, and it's always pairs of something between 40 and 7F, we will automatically get labels in that area that are not real labels, but that have to be, that are indications of something being interpreted as code, though it is text. So let's use these and turn them into string. Yeah, and it even continues. We have here format set to string. And with that, we have eliminated quite a number of labels in this area of 40. So what we can do, we can actually turn all of this into data space. Yeah, indicate that this should all be data. The pattern that we see here is probably from some kind of memory test, or it's some kind of initial fill process that syncalc performs on the extended memory banks. And we know that the extended memory bank ends here, and that everything in here definitely is just some data storage. And with this, we get now all the labels that are seen to be in that area, and we know that there can't be labels like this. Yeah, so if something points to 4076 and we go here, then this actually has to be wrong. So here I'm not 100% sure what the right thing is, but it doesn't make sense for it to be. Is there something else where this goes to? No, this label is unloosed. Well, I'm here not 100% sure. It could be some self-modifying code. So let's go back to the area of 4000. See what other labels we have. Yeah, and here clearly you see it from the crap code up here that this must be text. So there is overlay, add, subtract, multiply, divide, always with an inverse character indicating the end of the string. There is drive 1, drive 2. All these are strings. Let's go back to the area of 4000. We see there are now fewer of these. Well, this is a kind of repetitive process that you have to go through, but it's worthwhile because in this case it quickly eliminates false positives for labels, and ultimately there should not be anything left in the area from 4000 to 7FFF. Well, I will pause the video, continue, and unpause when I'm back.